Monday. Uh, so we talked Monday about these stabilized islets and talked about uh, how to increase the selectivity. And one of the ways that we talked about, excuse me, of increasing selectivity was to use like kind of substrates where you could induce like a A13 interaction, which would disfavor one transition state over the other, like that. But let's talk more about the stabilized islets, and we're going to talk today about the Horner-Emmons reaction, which is a very, very slick way to introduce ester functionalities and make these alpha beta unsaturated esters and high trans selectivity. So let's talk about it. We're gonna talk about the mechanism and how the Horner-Emmons reaction can be used again to your advantage to make these highly trans selective. Hold on one second. Yes, Jim.
Do you know the passwords for the present set?
It's the same as the other one. I'll have to text it to you.
No, I have it. I
It's,
have it.
yeah, it's the same password.
Okay.
All right.
Bye.
Bye. Sorry about that. YouTube will be hearing all our conversations, but it's okay. Part of life. All right, so let's talk about that. Horner Emmons. Actually, it's Horner Wadsworth Emmons. Let me fix that. All right, so the Horner Wadsworth Emmons reaction, and that is using these are phosphorus stabilized islets, right? So you have a uh, phosphine oxide. Right, so this is your islet right here. There's also a phosphine oxide islet that they use that looks like this. Sorry about that. I can't find my little palm glove, so I'm back to being a caveman today. All right, so both of those are highly trans selective, right? Highly trans selective, and they're more reactive than your regular phosphine islet. So let me show you an example here, right? So you take the um, so you take your phosphodiester and treat it with a strong base. Obviously, you have to deprotonate this site right here. So that's the first step is to treat this with a strong base. In this particular case is KHMDS, and that's a nitrogen base. I can show you what it looks like too. It looks like this. And it's got two silicon groups on it. The stylus is sticking like that. So though it's a potassium hexamethyl disilazane. That's the what the KHMDS is. So that's a strong base that's going to do your depronation, and then you just follow that up with the aldehyde at minus 78 degrees Celsius. All right, and then from there you get a let me draw it down here, a trans alpha beta unsaturated ester 95 to 5 trans to cis. Let me zoom in so I can fix that. So this is the major product, right? The trans. You see the alkene right here is trans, and it's 95 to 5. Right? And so the reason why you see this high trans selectivity, this is how they explain it, is that the formation of the, well, not the beta-ene, but the oxyphosphatane, right? That step is fast for the cis oxyphosphatane and slow for the trans. So let's talk about that. Uh, so of course you start with this. Plus your aldehyde, and it's believed that it's the aldehyde approach to the illite that sets your stereochemistry, right? So that sets whether or not it's going to be cis or trans. We've already talked about those different transition states. Well, you have those Parker transition states, and the cis and trans is going to be based on the interactions in those transition states between your substituents. All right, so now you have, so the cyclization part is fast for the cis, and I'm gonna draw this as a beta ene, even though we already discussed the fact that it's not necessarily going through that. All right, so that's that, and then you have your R group from your aldehyde, and you have your ester, right? And then you get, I'm just gonna copy this, cheat a little bit, and I'm gonna shrink it down too. So this is the trans intermediate. So this what they're proposing is that the cyclization part, so this part from here to here for the cis is faster than it is for the trans. So this is the fast step. And then for the trans, it happens to be the slow step or the rate determinant step, right? And there can be some interconversion between cis and trans also. So they're also proposing that the cis and the trans are in equilibrium with one another, right? But then the actual let me back up. So the actual cyclization part, let me back up. So the approach and the formation of this intermediate is fast for the cis and it's slow for the trans. But then the actual cyclization part is slow for the cis and it's fast for the trans. Right. So the first step, the addition step, is fast for cis and slow for trans. And then the actual cyclization and then decomposition is faster for the trans than it is for the cis. So let me put that here, and I'm just gonna just write it like so. So that's the cis, and then over here, that's the trans. So this part, and then the decomposition, right? So the oxyphosphatane cyclization part and the decomposition for the cis is slower than it is for the trans. All right, and so that's the explanation they give for um that's the explanation they give for the difference in the stereo selection for this particular type of illid and this reaction. Um, there's another perturbation of this. Let me pull it up because I forgot to grab this the other day. But let me pull up uh, the organic chemistry portal, and then there's another reaction in this same vein. It's called the Clark-Steele reaction. So let me see if I can pull it up on here. Any questions so far? All right. Let me find the Clark-Steele reaction. Um, because it's a way to favor the cis over the trans using a similar type illid, but with a different with some different functionality. Let me try something else. I should have grabbed this earlier. It's here. So the Clark-Steele variant is right here. right? And I normally, this is not something I normally would do. I should have had this already pulled up, but the Clark steel, you can see. Let me see if I can export this. So you can see in that bottom illet, it's or the bottom phosphodiester. It's a similar species, but the only difference is those tetrafluoral methyl groups that are attached. Can y'all see that? So
Yes.
let me see if I can copy this and put it into our notes. Let's see. Boom. Boy, I tell you, God is good all the time. All the time, God is good. All right, so this Clark steel modification, what happens when you add in those CF3 groups is you further polarize that phosphine ester, right? And so what happens is, as opposed to the Horner-Wadsworth reaction, which is shown up here, where you have uh, the addition part being fast for the cis and slow for the trans, but then the cyclization and decomposition being slow, the CF3 groups that are attached to your phosphoester actually increase the rate for the cis of those slow steps. And that's why for the Clark steel, you can, I'm sorry, for the Clark steel modification, you look at the selectivity, it's 50 to 1 for the cis, right? So I'm gonna write that in here. So that modification increases the rate of cyclization as well as decomposition. Um, and the fact that you increase the rate of cyclization and decomposition for the cis oxyphosphate. Let me put that in there. Not this. Right, you're able to increase the amount of. Actually, you're able to flip the selectivity and start to favor the cis over the trans. And you can imagine making the phosphorus more electron poor by putting those trifluoromethyl groups onto phosphorus. um, that that makes phosphorus more reactive, right? And so that slow step for the cis increases because of the increased reactivity of phosphorus in that re-enclosure. So uh, that's a way to again use to your advantage if you want a cis alkene in the product, then you can use the Clark steel modification. If you want this type of alkene where you get this alpha beta unsaturated ester, you can use the Clark steel modification because these alpha beta unsaturated esters are important precursors to all types of other uh, structures, right, or molecular motifs, right. So that's between the Clark steel and the Horner-Wadsworth Emmons, right. You're able to get either cis or trans alpha beta unsaturated esters, depending on uh, what your preference is. And the reason that's important is because again, uh, when you're doing synthesis, sometimes you need a trans alkene in the product, or a trans alpha beta unsaturated ester, or a alpha beta unsaturated ester. And so if that's the case, then you need a tool to be able to do that. Everything goes back to uh, the tools at hand, right, that you have. And so you need those different tools in order to be able to do that. All right. Any questions about anything so far?
No, sir.
All right. Let me show you a an example where this was used in a synthesis to actually build up a chain or precursor to be added into another synthetic piece to build up a natural product. So let me show you that. And let me see something right quick. Um, I want to see if I can pull up this. I think I downloaded this book. Let me see if I have it because I want to show you. I don't know if it's on my Kindle or on my Google Books. Never mind. So here's an example of again building up precursors to natural products using these reactions. I always like to give some type of examples with this. So this is an example by Bushelli. And it's in tetrahedron letters. This is from 1985. It's an old example, but still relevant nonetheless. Uh, volume 26 and page 5239. Come on, man. All right, so they started out with this really highly functionalized alkyl chain, like a diol. And I'm gonna show you that. So you have a bunch of, and I think this is a good place to talk about protecting groups also. So I'm gonna mention that too. Fix this right quick. So you got this really complicated aldehyde. All these stereo centers on the backbone, and then they looked at converting this aldehyde into a trans alpha beta unsaturated uh, ester. So they took this ester here, or this phosphodiester that they later converted into an illite. And I'm gonna write So this thing is conjugated. She got 5 alkenes in between, and there's an ester on the end. And so in the product, right, you have, of course, this aldehyde is going to get converted into an alkene, a trans alkene, because they're using this Horner-Wadsworth technology. And then the rest of the stereochemistry, I'm going to show you. They have a table here. Uh, right there's an ester on the end here. I just cut it off. All right. And so for your R groups on your illet right here, highlight them. The selectivity changes based on what that R group is. Right. If that's a methyl, then it's the sister trans ratio is 1.2 to 1. If it's ethyl, then it is 1.75 to 1. Which is counterintuitive, right? Because this shouldn't be a cis selective, but that's not a huge difference. But it shouldn't be a cis selective process. But when they increase the bulk of the R group uh, to something like an isopropyl, then it's only trans, right? 100 to 0. And then uh, if they increase the bulk even further, right, to this diethyl, then it's also 100 to 0. So what you see from this example is not only the utility, but also the fact that the reaction itself is tolerant to a lot of different functional groups. Like you can have highly functionalized substrates and still do that olefination reaction with no problem. So let me talk for 1 second about the groups here, like what we saw, uh, OTBS or OTES, right? Those these groups here, TBS, TES, these are what we call protecting groups. Right? That you can protect different atoms. You can protect alcohols, you can protect carbonyls, you can protect nitrogens. It just depends on um, like what functional group you want to keep from reacting. So protecting groups, but what we use them for is to stop unwanted side reactions. Right. So if we got functional groups that we don't want to react, then we use some type of protecting group on them. All right. So we have an alcohol. like this, right? The way you add a protecting group, a silicon protecting group, because those are silicon protecting groups. There are a lot of different types. Um, we'll probably talk more about that on Friday, and then jump back and cover a couple of more olefination reactions, and then we'll move on to those triple bonds. Uh, but if you want to protect it, like you'll use like a some type of solid chloride, and then a base like pyridine or imidazole or something like that. So pyridine to do proton transfer and take off the OH proton, and then I don't know what's going on with this stylus, man. Come on, bro. All right, so pyridine, or imidazole, either one, with a solid chloride and alcohol, and what happens is you end up with a silylated oxygen, right? And we'll just say plus HCl, right? Because that pyridine, once it does proton transfer, it's going to transfer that proton back to something. So you end up with that plus HCl. All right. And so what this does is it keeps that oxygen from being able to react, right? The oxygen can't react with another functional group. It can't react with another species because it's coupled up now with this silicon. So let me give you some of the more common ones. So TBS is tert-butyl silane. So that is a silicon with three tert-butyl groups attached to it. And then whatever your leaving group is. Chlorine. Most of the time it's going to be a solid chloride. Those are or solid triflate. Right? It's going to be chlorine or a triflate. And then uh, TMS is also fairly common, and that's just a silicon with three methyl groups attached to it. So trimethylsilane. There's another one, TBDMS. So tert-butyl dimethylsilane. So all these different silane protecting groups are able to, again, you cap off your alcohol, and then TES, which is one of the ones shown in the example, is triethylsilane. Right, and X again is whatever your leaving group is, chlorine or a triflate, or it depends on like what you're trying to do. All right, and all of these protecting groups have different reactivity, and when it's time to take them off, for your solid protecting groups, you can just use something like hydrofluoric acid. All right, let me see if I can put that in. I hate to put that on a separate page. So you can remove them with HF. And these are using HF is tricky because you can't use it in glass. You got to use it in plastic. So a lot of times when you do your deep protection, you'll do it in like a Nalgene vial or something like Teflon coated vial, so you don't etch out the glass in a round bottom glass. But you can remove most of your silicon protecting groups with HF. So we're going to talk about some other protecting groups on Friday. I got a whole little section on that. Uh, but the point is, again, to go back to the original point, the Horner-Wadsworth-Emmons reaction, as well as the Clark-Steele modification, both both tolerant of like functionality being in your substrate. And then the sub point is that sometimes you have to use these protecting groups in order to keep your functional groups on your substrate from reacting with other things in the reaction mixture. So, any questions about that?
No.
All right, so we've seen phosphorus islets. We've seen these phosphodiester islets. We talked about the Schlosser modification, and I want to introduce you to one other method, um, and that is the Julia coupling, which is another olefination method. All right, so Julia coupling uses a different type of illet. It uses a sulfone illet, and this is a highly trans-selective reaction. Right. So let me show you the seminal example of this. So you have an aldehyde like this, and plus this sulfone. Right, and you can imagine these protons right here. That's on my illet. That's why I'm gonna. That's the carbon where my illet is going to be formed, right? Because those protons they have a pK of about 23, so they can be pulled off with a strong base, right? So you can pull off one of these protons and get the corresponding illet, and you can write that down here. All right, so that's the carbon that's going to react, and so your um, reaction with the aldehyde is going to take place there, right? That's what's going to attack your aldehyde or your ketone. Uh, and let me show you the reaction conditions because this is a little bit more. It's a little bit more detailed than some of the other reactions because you got a few more reagents, and there's a reason. I'm gonna show you why. So you have your aldehyde, and then obviously plus your Julia reagent. And then you do this with LDA, which is a really strong base. And then uh, so LDA, and then you follow that up with acetic anhydride. Stylus is killing me. All right, so acetic anhydride, and then sodium amalgam. So it's a sodium mercury mixture. And this is after you isolate this sulfone uh, additive. So that's what the acetic anhydride is there for. It's basically a way to trap the uh, the betaine species, right? And so, but the outcome is a highly trans-selective reaction. So this is the aldehyde we started with, and it's 80 to 1 in favor of the trans isomer, right? So let's look at how this works, like the mechanism, and then we'll stop here, right? So obviously the first step is the addition of the illet to the aldehyde. And it's not really a illet in a traditional sense because there's no charge on sulfur. Uh, but it's the same, it's in the same, uh, it's the same concept or the same idea. So this is my illet plus my aldehyde, which is going to attack here. Again, this is just a simple addition. And from that, I'm going to get this intermediate sulfone. Right, and then I use the acetic anhydride to trap that. And I add in some DMAP. Right, so that's going to give me this intermediate. And what you see right now is that this is really set up. If we did the elimination, right, this is set up to be a cis alkene, but the elimination doesn't happen here, right? That's the part. That's the role of the sodium, which I'm going to show you in a second. So when you treat this intermediate right here with that sodium amalgam, it generates a carbanion on that carbon where your sulfone is. So when you it's sodium amalgam is used to remove that sulfone. Hopefully you can follow this. My crazy arrows. So when you treat that with that sodium amalgam, you end up here. Right. So you got a carbanion there. And then you go back to your original, the very first idea that we let me fix that p orbital. The very first idea that we talked about with the Peterson olefination, right? What type of elimination you can get, right? You can get, it can eliminate syn periplanar or anti-periplanar. So if this intermediate, now you got a competition between how it eliminates. And this goes back to what we talked about with that Peterson olefination, right? If it eliminates in an anti-periplanar fashion, that means you're going to have some bond rotation so that the acetate uh, functional group is pointed down, and now the lone pair is here, and you just donate here and eliminate right into that, donate into that CO sigma star orbital, right? And this would be, I'm gonna abbreviate this, anti-periplanar. And then if it's syn periplanar, then there's no bond rotation. That's how you get the cis, by simply eliminating here and then here. So to get syn periplanar elimination. So it depends on the type of elimination. Uh, but how would you explain the trans being predominant, even though uh, the cis is possible and you get some of it? How would you explain that, considering you got to go through uh, a bond rotation to even get in the right geometry for the trans to be formed? What do you think? Right, think about it in terms of a competition. A competition. All right, and this is one of the again one of the more nuanced ways of thinking about mechanisms. Right, how is the trans favored over the cis in this case, and it has to go undergo a bond rotation before it can even eliminate? Anybody?
Just knowing that molecules prefer to be in their lowest energy state. I'm guessing there's going to be some type of, I guess you could say, interaction hindrance because of the R group and that other. This,
On the, you mean on the cis?
yeah, on the cis, just the interaction between the R group and this other. Is this an isopropyl group?
Yeah. Okay. I like that. I like that idea, but this is a it's a it's kind of more of a rate argument. So think about it. If the trans is predominant over the cis, then that must mean that bond rotation and elimination for the trans species is happening faster than just the elimination for the cis, right? That's it's probably more of an electronic factor as well, because if you look in the trans, you can see right here that CO sigma star orbital that's going to be kind of jutted out this way. Let me see if I can draw that in there in a different color. So this is going to be your sigma star. Right, that's where you have to donate in order to get that acetate group to leave. You can see that that geometry is going to probably be energetically more favorable, because if the sigma star is already properly aligned, right, it's gonna more likely undergo that bond rotation really quickly to get to that geometry. While the cis, you can see the sigma star and the P is not necessarily properly aligned for overlap. So you can have overlap, but it won't be good overlap like this. All right. So if I were to draw in the sigma star here, right, you can see that that overlap is not as good, right? But here you can donate right into it. You following in the trans. So the trans The bond rotation and the elimination is faster than the cis elimination in itself. And that's why you see that the product being predominantly trans. And I'm gonna put down here possibly due to orbital overlap. If I can write, come on, pen. I don't know if it's my hand or the pen. So I'm just gonna say P sigma star overlap. And let me shrink that down so it'll fit and won't get cut off. Yeah, so it's probably an electronic factor more than it is a steric factor. But you're right in the sense that the trans is a more stable species because the groups on opposite sides to one another or of one another. All right. Any questions about that, about the Julia coupling, or about anything we talked about? Let me put a date on this. All right. No questions?
Sorry about that.
That's okay. All right. We're gonna stop here. We'll pick this up on Friday. I'm gonna find a couple of good papers for you to grab and present on Friday. Who and so I think the first time we did it, Jonathan went first, and then last time Sam went first. So on this Friday, it'll be ladies first, like Queen Latifah. Y'all probably don't remember that song, or you might.